This is Russ Muller. I'm an Area Technology Manager for the Rosemont Measurement Division of Emerson Process Management. This is a recap or re-recording of a presentation that was done throughout New England in May of 2012. Today's presentation is, as the title says, Measurement Knowledge is Power, Increase Yours. In the live seminars, as they were given, we had this agenda slide was common to all presentations, where the business challenges that are kind of common across industries, it doesn't make any difference which industry you're in, were addressed, and each one of the 8 presenters had their particular slant on addressing these business challenges. And what I did on that day was say, look, doing more with less and global and intra-company competition are more directly addressed by this presentation on knowledge is power than energy and the others. As most people realize, there is not a cut and dry dividing line on any given topic. This particular presentation could just as easily have something to say about energy and compliance with increasing regulations, but we're going to do concentrate on doing more with less in competition. So what I said on that day, and I still say today, to put it another way, and this is a quote from a very, very advanced player in all digital protocols. If your enterprise values stable, safe processes that stay online when your neighbors are shutting down due to spurious trips, freeze-ups, and other unforeseen instrumentalities, then there's great value to be derived from integrated device intelligence. That link, and if anybody ever requests this, that link is live to Control Global. Jen Rezovic is a contributing editor and has a monthly column called On the Bus, and very, very worthwhile reading to. But look, think about what he's saying there. If you're not using integrated device intelligence, or we use the term plant asset management or asset management in general, you're putting your company at a competitive disadvantage to people who are actually doing that. And if we consider not just one person's opinion, but from ISA, 10% of maintenance work is actually harmful. The implication of that is enormous, because the way everybody does things now is sort of ad hoc. A problem arises and we go check it out, and there's a time delay always. And sometimes we're executing preventive maintenance steps and we're actually making things worse, and that's what this 10% refers to. And once again, that's from ISA. That's not one person's opinion. Dow Chemical further found, and this was just Dow, this survey has been completed many times since, that nearly 2/3 of all instrumentation work orders essentially were a waste of time. A waste of time and money. So what we want to conclude from all of this is that what's shown in that graphic on the lower right-hand corner is kind of the old way. This is, and it's also the most common way that we still do things today. We have a problem. Operators report that something's out of whack. First thing that somebody has to do is generate a work order for a technician to go out and touch the instrument. And the very first question they need to ask themselves, and the question that needs answering is the indication that the operator got the instrument going awry, or is it the process going awry? But think about the time delay built into today's process. Operator sees a problem, generates a work order, the work order goes into the queue. When the technician gets around to executing that one, goes out and executes it, unless, of course, this is an emergency breakdown. But there's still a time delay. So what we want to do is move from that old model to this model, where somebody can click on an icon, one mouse click, and see this. And what this is an attempt by Emerson to reduce increasingly complex technology, even 420 milliamp with HART devices, and this actually is a field bus device, but that gets even more interesting, doesn't it, if you're doing foundation field bus, perceived to be very, very difficult, but it isn't. And here it is reduced to a single mouse click. And on this, what we call the dashboard, at a glance, the operator or the person at the asset management workstation can tell, number one, the device is good. So if you're getting a negative indication, it isn't the device. In the upper right-hand corner, that mode, in service, the device is in service. Had this been a wired instrument, there would have been no indication there, but had this been a wireless HART instrument, it would have said connected or polled or whatever. There would have been an indication that what you're seeing is in real time and it's up to date and it's good. And right below that, of course, are the representations of the process variables, however many are applicable to the instrument. And below that, we see some shortcuts, so that once again, this is being the faceplate for a foundation field bus instrument. Once again, people think, ooh, FF, that's complicated. No, what we're doing is reducing the things that you want to be able to do down to more mouse clicks. But the main point of this slide is in that box in the upper right-hand corner. 63% of use cases, that 2/3 that Dow found, are reduced to a single mouse click. I can see, do I have to go out there? If I don't, I've just answered my problem, folks. It's the process. It's not the instrument. The instrument believes everything's okay. So you've answered that question in seconds rather than minutes or hours. If we want to do that, that happened to be a pressure instrument. We want to, can we do this only on pressure instruments? No, of course not. We can do this on virtually every field device that Emerson makes. This is actually not proprietary technology to Emerson. It's just that Emerson has taken more advantage of taking the intelligence that comes from a smart instrument of any protocol and presenting it in a user-friendly manner, especially in a manner to someone who may have just started at your business last week. They can get the same benefit out of working with our instruments that an old hand can get because of that interface, and it applies to all instruments. Here is the basic philosophy. You can see my cursor circling the field device, and since the very beginning of intelligent instrumentation, and that would begin with Honeywell DE, DE standing for digitally enhanced. Honeywell was the first instrumentation automation vendor who actually put a microprocessor into a field instrument so that you could query the instrument for its health. You used a handheld tool. So you can see that the model that we showed with the brand's shiny new 475 field communicator a couple of slides ago is not new technology, it's just that the tool is new. And in this particular case, the method is new as well. Back then, what we were checking for was the health of the field device, and today we're checking for the health of the field device. That's the root of the model. What we are trying to say is that field devices have gotten so smart, and the advance of microprocessor technology has proceeded so far since the early 1980s when DE came out, that now the device is capable of monitoring not only its own health, but also the loop power, what the host is seeing, the connection, and actually some intelligence about the process. So what we want then is, and here is the fully developed model, not just device health, but everything that instrument touches, from the process all the way back to the host, and we want to make it easy to use. So that's where your payoff comes in. So if we look at process intelligence and connection, what we're really trying to do is look for things that are happening in the process at that point. That process connection, is that process connection connected to the process and the line that's connecting it plugged? Are things in the process going awry? Do I have an unstable flame in a fired heater and I'm still continuing to feed fuel into it? What could be the ramifications of that? Can I operate a distillation column more efficiently by operating it closer to the point of flooding, which is the most efficient place to operate it? Process leakage. It could be the process connections themselves or leakage themselves. So once again, without going too much further into this, I want to be able to see more and more. The instruments have that ability to do, and everyone out there who has ever installed an instrument, who is ever from the very beginning of the process thinking about, gee, it would be better for the business if we had a measurement at this point, to the point where you actually flip the switch and you have the measurement, you know exactly what that costs, because it will be higher, say, in life sciences, or maybe in a refinery application. It might not be so high in a facility that is not large in size and scale. But no matter, the cost of installing point becomes more easily justified and better amortized if you get more information out of that point. So here's what we're getting to. Any instrument, no matter who made it, no matter how fast it updates, if it is connected to a host, the information that the operators are going to get, that the host will see, is governed by how fast the host updates. The device, however, which in the case of this instrument, in the case of a lot of our instruments, updates 22 times a second, every 40 milliseconds. So the granularity of the information that the instrument can actually present you is very, very high.
Welcome to GoToWebinar, Web Events Made Easy. Welcome to the webinar. You have entered as an organizer and may now speak to any other organizers or panelists on the line. When you are ready to begin the presentation, press *1 to allow all attendees to hear you. This system will notify you once you begin your broadcast.
The steam line has dropped below the temperature of saturation, and now I am raining condensate horizontally. I'm essentially firing bullets at the orifice plate. What that increased noise signal is showing is the instrument sees it. What this unvarying process variable is showing is the operator doesn't see it. But what this increased standard deviation is showing is the instrument not only sees it, but it is now in a position to be able to tell you that it's seeing it. Same with a plugged impulse line. Even though the upstand on this is very, very short, it still is an impact line. There still is a tap in the corner of the orifice plate holder. If one of those taps gets plugged, funny thing happens. The pressure that was trapped between the plug and the sensor, which is actually up in here, was captured. The variable will not change. That pressure that was captured by the closed plug will always be there, and if the flowing level has not changed, the process is not reporting a change in its variable, and the operator does not see it, but the instrument sees it, because the instrument is interpreting this low level of noise as a low process noise, a low standard deviation. Our instrument, if we look into our online asset manager, is actually showing us. Let's scale this up a little bit. In a second, we'll show you that what we've done is we've plugged the line, the standard deviation has gone below this gray line, which was set when the operator or the instrument engineer set up this instrument. We'll show you in a little bit that this is a repetitive process to fine-tune this. We're also showing that we have some controls over this, that we can reset if we have a change in condition, and we can reset, we can tell the instrument to go learn again. But in big scale, this is what this looks like. Now, you would not normally expose this, however, because you would not normally be sitting staring at an asset manager screen. But you can. This instrument is actually capable of reporting standard deviation as a variable, second, third, or fourth variable, which could be turned into DCS, and it can see this. A little time delay there. It's slower to report than the instrument is. However, it can be reported, but the fact that the instrument can measure it and report it is the key. Now, here's a case where somebody actually used this. This is a chemical, I think it's Mitsubishi Chemicals in Japan, did a report a few years ago where they were having a control valve. Here's the very, very simple loop. But I'm controlling pumps. And actually what I'm doing is I'm controlling a bank of 3 pumps. And I'm measuring flow. And what I'm seeing is, and this is what they actually saw, this is an actual live case, where an abnormal situation occurred where we have a spike in standard deviation, and yet we have a drop-off in valve position at the same time. So what is causing that? So this was the presenter going through the steps of what we are monitoring and what we think it is. So we think maybe it's could be a valve. Everybody suspects the instrument, suspects the valve first. We are getting an indication that is opposite to what we expect, so what could be causing this. So let's go through this just a little bit more. So my standard deviation jumps when the flow rate drops and the pump motor rates drop. So, gee, this is awfully strange. What? Hey, wait a minute. If the pump has got air entrained in it, is it possibly damping the measurement, damping the response? So in this particular case, what they were able to back figure, so now they have their root cause because the instrument could give them enough clues to be able to figure this out, that if we get air in the lines, our measurements are off. The entrained air acts like a damper itself. That's making the standard deviation drop. It's not kind of like a plug line, but it is because it's damping the pressure signal. And the instrument was able to spot it in the first case. So what else can statistical process monitoring do? We can, here's that air entrainment in the liquid flow line. Agitation, the agitator either stops or drops a blade. Catalyst circulation, there at ExxonMobil has done a white paper on this that's published. We can make available actually, where the commission noticed stick slip, circulation of catalyst in the fluidized cracker stopped. And in the real world case, they figured that they had about 20 minutes to figure out what was going on, or they were going to have to bring the cracker down at a cost of millions of dollars a day in downtime, plus all the dangers involved in bringing a big system down and then bringing it back up. Plugged lines, distillation column, furnace flame instability, we talked about that a little bit. Maybe a steam trap failure, maybe a valve cavitating. Any process that has a steady state condition that can be trended, the fastest trend is kept in the instrument, and now the instrument is capable of reporting it. So, but how do we make use of this? So we have a 4-step model that we talk about for turning what the instrument can now see into information that you can use. So the first thing is to recognize what the instrument is capable of measuring and interpreting. So standard deviation of the process variable, the mean of the process variable, and a brand new one, coefficient of variation, which is the ratio of standard deviation to mean. coefficient of variation is useful in the flowing line where the flow is expected to change. Where you expect the flow to change, you do not expect the coefficient of variation to change. That's what that variable is all about. So the second thing is, knowing that the instruments can do this, what do we have in our process where an up to the second process touch can add value to our business? Do we have things that can be measured? Let's see. So now what we do is we decide on how to implement, and then we set some alerts. And then we go in and we interpret those alerts, and we see, remember those gray lines on the graph I showed you a little bit before? Where do we set those limits? If we set them too tight, we're going to plague the operators with excess alarms. If we set them too loose, we may miss something. So this four-step iterative process allows us to fine-tune the use of the diagnostic by the application, and to learn more and more about how our process works at a finer and finer level of granularity. And once again, it is not just the process connect. It's not just the instrument. It's not just the process connections, the primary elements. It's also what's going on in the process itself. The instrument is capable of maintaining data within itself, so that actions that have been taken or that it has detected are logged in the instrument and can go back and are accessible from either a handheld put on at the local right at the instrument, or all the way back to the host with just mouse clicks, and capturing the instrumentation's onboard intelligence. I am capable of trending more than one variable. In this particular case, this is a pressure instrument that also has a temperature associated with it. All smart instruments, by the way, have an onboard temperature sensor. That's part of what makes them smart. It's part of how they do their correction routine. What we do is we expose that as a variable, and so now you have a second variable, and oh, by the way, you can monitor it as well. So is the tracing on when it shouldn't be? Did the tracing go off when it should be? When did it go off? What might have caused that to happen? We log the event. We can also log some useful information in the instruments itself. Field bus instruments actually have the ability to log the last calibration event in them. They just have that much processing power. So now here we are. We have taken care of this. We've addressed this end of the loop. Now let's take a look at this end of the loop, from the instrument back to the host, and that's loop integrity. If you've ever had the experience of, this is the one that everybody knows about, water in the terminal compartment. I have to tell you, folks, in all of the various, and I have been in every type of process that you can imagine across the United States, in all of the various places that I have visited, I have never yet found an instance where they didn't have this happen once. Somebody opens the terminal cover and water comes out. Either bad connections, unsealed conduit entries, the condensate in the conduit running back into the terminals. When that happens, a not good thing happens. The loop is perturbed. One of the things that is a universal truth about 4 to 20 milliamp instrumentation is that the measurement is almost always going to be there, but you may or may not be getting a good measurement because of these effects, things that happen in the loop. A digital instrument, whether it is wired or wireless, if you have the measurement, it is perfect. The problem with digital instrumentation is you may not always have the measurement. If you don't have the measurement in a digital architecture, it is 98% of the time it's a problem in the installation, which can be corrected, and most of them can be corrected at the time of installation. But generally, your field research in troubleshooting in digital architecture will be connection and communication. There is not the possibility of water getting in the terminal and changing the output. I can tell you, and I've done this even with distilled water, when the distilled water touches those terminal screws, the milliamp output of the transmitter as received by the host changes. not very much, but with distilled water, but with water that has lain in a galvanized steel conduit or has lain in our aluminum alloy housing for any length of time before it gets up to there, is just loaded with ions. And I get myself a nice, sweet secondary conductivity path through that water, and your milliamps go wild, and it's uncontrollable. You cannot see what the difference is. It has to be measured, but you have to know to measure. The instrument is capable of doing that. But even further, maybe I've opened a terminal cover too many times in an atmosphere where I shouldn't have been opening it at all. Maybe I've got vibration fraying my connections. Maybe my power supply is going funky. All of those things will change what the control host believes it's seeing from the instrument, even though the instrument knows better. Now, Part 7, which is a discussion for another day, is retrofitting a way to detect that. But instruments that have been built in the last 5 years that are not Part 7 have this built in, and or can have this built in, or they can have it added. So this is a discussion to have with your instrumentation account manager. So anyway, here's how the power diagnostic works. We establish a 420 milliamp point, and the instrument is set into a learn mode, or actually that it's characterized the loop, and the instrument sits there and it goes, okay, I understand it should sleep. So okay, now I'm good. Now it's constantly doing this, and at some point it gets an excursion from one of those causes on the prior slide, and at that point it reports a problem. Now the problem can be an alert, which resets when the alert clears. It can be alert which latches and it stays there until it makes you go look, or it can actually drive an alarm output. I can drive a failure output. I can put the instrument at 3.8 milliamps, in which you know to go look right now because the instrument is, but you can go in and see that that alert has been triggered. There is actually an implication for this alert if you have a safety instrumented system. If you don't have a safety instrumented system, you can stare out the window for the next 20 seconds. But if you do have a safety instrumented system, that loop diagnostic has been proven to, by Exida, to actually have a positive impact on proof testing, where proof testing interval can be extended from 5 to 10 years because that diagnostic is installed, and it's a very large instance out of taking the word undetected out of undetected failures. It's a failure that is now detectable. Okay, that's why that slow level can be increased. That's the implication of this side. Once again, I'm assuming most people do not have SIS in New England, and so I'm going to not spend too much time. If you want, we can actually get this presentation into your hands. So we are now covering from one end to the other, the complete loop, but now we want to make it easy to use. So here's that part. How do we get it? That's always a big question, and we're showing device screens from Emerson's AMS, Asset Management Software, which has all of this built in. There are other asset management packages available that are either EDDL based, which AMS is, and I'm not going to go into what the acronyms mean, or there's a newer one called, or there's a different one actually called FDT-DTM, uses an FDT frame. You might recognize Field Care, or what is Honeywell called? There's PDM, FDM, Field Device Manager. The various different manufacturers. Rockwell has the Factory Talk Asset Center. That is a DTM base. Doesn't make any difference. No matter what software you choose to do interpretation, this works exactly the same. It looks exactly the same. Don't have an online asset manager and not intending to implement one, we can use a heart signal splitter. We can put the device into talk mode. The actual technical term is burst mode. And so the instrument is now bursting second, third, and fourth variables, one of which can be an alert for one of these diagnostics. and receive it, wire it in, and receive it as a variable in the host. It's always, the old model will always work, and that is go out and touch it with a field instrument. If I have a hard-enabled host, and more hosts are heart smart, Alan Bradley is doing a pretty good job of putting heart-enabled AI and AO, DI and DO cards for their various logics control hosts. And then the newest way to get all of this is to pick and choose. Pick the ones you want to implement and make them wireless. So you apply a heart wireless adapter. We use the four-letter acronym THUMB, but the generic term is wireless heart adapter. And apply it onto a standard heart-speaking instrument, and it will go on any heart-speaking instrument made by any manufacturer since the beginning of heart, which is the late 80s. And it will convert it into a wireless instrument, and it will allow the gateway to receive the information and receive it and report it and latch it and hold it, and it's a very, very elegant and very, very low-cost way to get this. So that's another path. So now what we've done, in summary, is we have looked at the entire loop. So here is your maximum amount of intelligence out of that field instrument, and we're showing you how we have made it easy to use. And once again, all of this has been based on a pressure instrument because Rosemount and pressure go perfect together. But all of our various different devices have some form of a trendable diagnostic that can be reported, so that things like signal trigger level, signal level being generated by the coils. In a level instrument, do I have a probe that's coding to the point where my signal level is being attenuated, and I'm going to have to pull it out and clean it. The device is going to tell you, yeah, and you can probably trend and say, next week, yeah, we can make it to the next outage. Okay. The instrument is telling you we can probably make it to the next outage. So now you can plan your work, and it applies to any smart instrument. Some of the devices that here's some coding with forks, very, very interesting, detecting the degradation of a thermocouple, detecting that RTDs are going out of whack. One of them has failed, and now I'm on my spare, and I don't have a backup. All of these diagnostics are available, and they work the same way that I've outlined for the body of this presentation. How do you get it all? Since they're virtually all Q is quaternary, the 2nd, 3rd, and 4th variable, I can use a signal splitter, the tri-loop that I can put a thumb on it, or I can expose the interface. And this is something that not a lot of people realize, but if you're using a wireless gateway, and I don't have one live right now, or you're using a digital interface because you have bus instrumentation, be it Profibus or Foundation Field Bus, and we make both, looking in the host interface itself will expose the variable information. You don't actually need software. The system is the software. The hardware is the software. The field devices are the software. They have it all on board. So this is my next to last slide. These white papers were made available at the presentation, and they can be made available to anyone who asks. We have a large file exchange. We put a couple of zip files up on the large file exchange, so you can hear when we're talking about our distillation column flooding and our flame instability. And proven results are, the white papers are how it works, and proven results are people talking about how they actually used it. So it might be interesting to somebody out there. And then finally, getting back to Emerson, whether it is through your local account manager for measurement, flow, valves and regulators, control host, getting to your local business partner, New England Controls. Any one of us, talking to any one of us is the same as talking to Wallace. And so let your friendly neighborhood Emerson contact know that you saw this stuff and you want to know more about it, and we will get you all the collateral and get you all the technical help you need to put it to use in your business. Thank you for tuning in. I hope you enjoy the rest of your day.